In this video, we will discuss the sampling distribution, which is a probability distribution of a statistic obtained from a large number of samples drawn from a specific population. In the previous video, we have discussed sampling approaches. It seems that we know how to obtain all those important statistics, such as mean and standard deviation about the population. The fact is, we do not know these parameters. Rather than we must estimate them from data because there exists sampling error. For example, the outcome will be different if we take another sample. So the difference between a sample statistic and its corresponding population parameter, which is defined as the sampling error. We can expect there to be sampling error between sample mean and standard deviation and the corresponding population mean and standard deviation. In this example, we assumed that we know the standard deviation of the distribution. Suppose that we have a population with a mean of 32, although we do not know that before sampling. However, when we draw samples with a sample size of 5 from the population 3 different times, we got a sample means of 31.6, 33.0, and 35.2, which are different from each other. In this sense, it is unlikely the mean of a sample will be exactly equal to the mean of the population. So how can we determine how accurate the sample mean is? In the next few slides, we will use the sampling distribution of the sample mean to help explain how we can rely on sample estimates. First, the sampling distribution of the mean is defined as the distribution of all possible sample means when you take a sample from the population. Theoretically, if you can obtain all potential samples, the mean of the sample means is exactly equal to the population mean. But in practice, we will never try to obtain all potential samples because it is even more costly to simply measure all items in the population. Second, for any data, as the sample size increases, the sampling distribution of the sample mean will converge to the normal distribution. This phenomenon is called the central limit theorem. According to central limit theorem, if all samples of a particular size are selected from any population, the sample distribution of the sample mean is approximately a normal distribution. This approximation improves with large samples. The central limit theorem is one of the most useful conclusions in statistics, and it's true for all population distributions. This allows us to use the normal probability distribution to create confidence intervals for the population mean and perform tests of hypotheses in the next module. There are several related properties regarding the sample size. First, if the population follows a normal probability distribution, then for any sample size, the sampling distribution of the sample mean will also be normal. If the population distribution is symmetrical, the distribution of the sample mean will look like a normal shape with samples as small as 10. For non-symmetric distribution, a sample of 30 or more will show the normality feature of the distribution of the sample mean. Therefore, if we do not know the distribution type of the population, it is safer to use a sample size of at least 30. For example, at the top of the chart here are 4 different population distributions Following each of these downward, we observe that the sample distributions appear more normal as sample size increase from 2 to 6 to 30. In other words, we observe the convergence to a normal distribution regardless of the shape of the population distribution. Similarly, we use standard deviation to measure the variation among sample means, which is also referred to as standard error. Even if we do not select all samples, we can expect the mean of the distribution of the sample means to be close to the population mean. If the population standard deviation is sigma, the standard deviation of the distribution of sample means is sigma divided by the square root of n. Because a sample size is typically more than 1, the dispersion of the sampling distribution of the sample mean is narrower than the population distribution. Note that when the sample size is increased, the standard error of the mean decreases. Following the definition of the z-score, we have z equal to x bar minus mu over sigma divided by square root of n. We now demonstrate on how to utilize the estimate of sampling distribution of sample means. In this example of cola soda bottling, the amount of cola in bottles follows normal distribution with a mean amount of cola in the bottles of 31.2 ounces and a standard deviation of 0.4 ounces. A technician randomly selected 16 bottles and obtained a sample mean of 31.38 ounces. The question is it likely the process is putting too much soda in the bottle? To answer the question, first, we need to find Z. Then we use the Z-score table to determine probability. The Z value is given by Z equal to x bar minus mu over sigma divided by square root of n equal to 31.38 minus 31.2 over 0.4 divided by square root of 16, which is equal to 1.8. Based on Z table, we find the probability of 0.4641 in this area, which suggests that the chance to have a mean higher than 31.38 is 0.5 minus 0.4641 equal to 0.0359. Therefore, based on a sample of 16 observations from the normal population with a mean of 31.2 ounces and a population standard deviation of 0.4 ounce, that it is unlikely, less than a 4% chance, that the sample mean equal to or greater than 31.38 ounces. We conclude that the process is putting too much cola in the bottles. The quality technician should see the production supervisor about reducing the amount of soda in each bottle. In summary, in this video, we introduced the concepts of sampling error in sampling distribution with long variance. We also discussed the sampling distribution of the sample means and study the central limit theorem, which is very important. Finally, we demonstrate how to use the sampling distribution.